going to measure the potential against. And we find, for instance, then, that this material, sodium, is going to be anodic to the hydrogen, and it's going to be anodic by 2.172 volts above this reference level. And on the other hand, hydrogen will really be anodic to gold, because gold is down at the bottom. There's another way to just think about it, or to state the chart, and I find it's easier to think about it this way myself, and that is to say that the more reactive metals are at the top of the chart, and the noble metals are at the bottom of the chart. So sodium is more reactive than is magnesium, than is beryllium, than is aluminum, than is manganese, and so on down the chart until we get all the way to the bottom, and we find that, let's just suppose we have something like copper and iron. Let's suppose we're going to use copper rivets to join iron together, and we want to know which one of them is going to corrode. Well, this would say that iron is anodic to copper, and we could take the differential to find out what the potential difference is in that particular material. And so if we put copper and iron in metallic contact now, if we just make a connection between the two, then the iron is going to corrode preferentially to the copper, or the copper is going to essentially make the iron corrode, is another way to look at it, if you put them in the same cell. So such a chart now is going to become all important to us, and I'm going to be referring back to that time and again in the next few things I want to tell you.
One feasible method of preventing corrosion involves adding voltage to oppose the flow of current in a corrosion cell. The Pourbaix diagram, which plots material pH versus imposed voltage, shows how imposing voltage can cause chemical immunity, passivation, or corrosion. Wet corrosion can also be termed solution corrosion, while dry corrosion may be termed compound formation. The Epstein experiment proved that without oxygen in an aqueous solution, corrosion cannot occur. A third type of corrosion, galvanic corrosion, occurs because members of the EMF series always become anodic to one another.
Let's suppose for a moment that we looked at something like a piece of road net. Let's suppose we took, say, some 1/8-inch wires and we welded them together in an orthogonal display. So we just have a network. And suppose we anneal this material so it is all exactly the same. There's no doubt now that I have one material and it's iron or steel of some composition, but it's all the same. And let's suppose I have a little thin box that I can fill with water, and I just immerse this iron network in the box. And I ask you, where do you think it would corrode first? At the crossover points of the wire, or in between the crossover points? Where would you think it would first corrode? Which one will disappear? Which one will dissolve, will just disintegrate, and I won't have any more material there? Between the crossover points, in a straight piece of wire, or right where they cross over? What do you think? Where they cross? Why? Actually, you're right. But why? Well, the reason is, although it's not shown on this chart that I have just displayed for you, the reason is that iron oxide, the material iron oxide, turns out to be cathodic to iron. That is to say, if I have iron oxide and iron together in a cell, then the iron is going to corrode preferentially. And it's going to be driven because we have connected the iron oxide and the iron. And the oxygen that's dissolving in the water is going to be distributed in the water by convection, and the convection is going to be minimized where the wires cross over. So there's going to be a concentration of oxygen in the midpoint, just because the oxygen can get to it first. And so that material will oxidize, and therefore at the crossover points we have developed now an anode, and we will start to dissolve it, and those little sections will disappear. This is called a concentration cell. In your text you will find a discussion of crevice corrosion. It proceeds by the same situation. If you starve a material, an area of the oxygen that's available, then it's going to become the anode in the material, in the ferrous-based material. And so we have concentration cells, and we have this wonderful little thing that goes like this. If I take a piece of material like copper, and let's say I cut it, it's a annealed piece of copper, I cut it half in two, and I take one half of that piece of copper, I put it on an anvil, and I beat the daylights out of it, right? I plastically deform it, I extrude it, wire draw it, whatever you want. But what is happening to the material? I change it. We looked at all of that before, right? It isn't the same thing as it was before. And do you know what? It becomes anodic to the annealed piece of copper. So if we put those two things in an electrolyte and connected them, it would be a perfectly good battery. It would be a low potential battery, but it would be a perfectly good battery, just because we plastically deform it. Now, this gives us a tremendous advantage in forensic metallurgy. And I'm sure if you've ever watched Quincy on TV, you've seen something like this, or maybe you've been involved yourself. Let's suppose I steal your gun, and I don't want it to be identified, so I file off the identification numbers that have been stamped in the surface. But when we stamp the surface, we plastically deform that number in. And although I file off the impression, the plastic deformation is still underneath. So in the forensic laboratory, in the laboratory, I can take that material, subject it to acidic attack. That means I put an electrolyte on it, right? And now the material that's plastically deformed, being anodic to the material that is not plastically deformed, begins to etch out. And I look and the numbers pop out for me. And so even though you've filed off the number, I can still read it, right? Well, this has tremendous import for us in a lot of things. And for instance, years ago, it is my understanding that in prosthesis, total stem prosthesis, that they had a problem with these little stems that at that time they were making out of austenitic stainless steel, and the manufacturer was proud of this thing that he could make, this little thing that he could stick in your hip and make you walk again. And so he wanted to identify it with a number, make sure you knew that it was his and where it came from, and he stamped the number in there. And then you put it in your body, and the body fluids, an electrolyte, cause attack to occur, and so we have a point of maximum attack. And you know what we do then? We build a little notch. And remember, we talked about those little notches before. Now in the generation of dislocation, and that's where fracture is going to occur, right? Fracture occurs at that particular point, and they found it to have hip prostheses that were breaking in people's legs just because they were walking. And so no longer do we do anything like that. We don't stamp those things in, and we make sure that whatever we do not cause an electropotential to be set up. So we have to be careful always of this, and yet we cannot do away with the point contact corrosion. If we have an electrolyte and we put this metallic material in it, and let's say the metallic material now is something like a piece of copper, and you just put it in seawater, you find out that the crystals are oriented differently, and that one of them is going to be an anode, another one a cathode, just as we saw in the first slides. And so you're going to have point corrosion always if you have a polycrystalline aggregate. And even if you had a single crystal, like a sphere of aluminum, and I told you about that, and you put it in an electrolyte and cause just tremendous corrosion to occur right away, then one face is going to dissolve preferentially to another face, right? And so it's going to drive that thing to some equilibrium shape, which was, in case of the aluminum single crystal, a cube. And so we find then that in this business of potential, we have an insidious sort of a thing in galvanic corrosion, because we have all these little batteries that are occurring, and as long as we have any electrolyte next to them, they're going to be active. Well, what do we learn out of this now that's going to enable us to prevent corrosion? Well, one of the things that we learned is that if I want to protect, let's say, underground piping, which is subject to a tremendous amount of corrosion, then I have a capability of doing something positive to really prevent the corrosion. I suppose one of the areas in the United States where we first recognized the severity of this problem was in Baltimore. Baltimore was the first gas-lit city in the United States, and that means that they had conduits or pipe that to put underground to the street lights to carry. These conduits carried the gas, and they lit the little light up. And so we have all these cast iron gas pipes in Baltimore. And the cast iron gas pipe in the ground actually would start to corrode by galvanic corrosion. Accelerated, by the way, by any time that it was connected with another pipe, another piping system, like a piece of copper pipe that may be put in that would touch it. Since there's always moisture in the soil, then we have this tremendous flow of current that would go between them. Not a tremendous flow of current, a very small flow of current, but over long, long periods of time. And so we have corrosion, actually within the material itself, within the cast iron. We find that we have graphite, and we have the material that is ferrite. And the ferrite actually was anodic to the graphite, so the ferrite would disappear, and we have these shells that are nothing more than graphite running through the ground in Baltimore. And that's all right because there's no great pressure on the gas. As long as you didn't disturb them, everything's fine. But you're going to build a new home, you run a trench, you excavate under it, you don't properly backfill it, a truck rolls over top, it cracks the pipe because it's just made out of graphite, and we have a problem, right? How do we prevent this? Well, what we do is we make sure that we can put something connected to it that's anodic to it. So we go to a field, the power companies own these little blocks or these areas, and they dig holes in the ground. And in these holes they put things like zinc electrodes or aluminum electrodes or anything that's high up on this EMF series table that I showed you, because those materials will be more active. And they electrically connect them. They wire them to the piping system. And there's a throwing power. They know how many blocks or how many hundreds or thousands of feet this will be effective. And then they have to put a new bed down to protect this underground corrosion that's going on. And the corrosion engineer can go to a site, dig a hole, and stick an electrode in the ground and measure the potential between the earth and the pipe that he wants to examine at that particular point and find out whether he has an effective protective system. Now this is called cathodic protection. I'm not sure that the word is really right, because to me police protection means that police protect the community, and therefore I think maybe they should call it anodic protection, but they don't. It's called cathodic protection. But it's done all the time, and it says if we want to protect a piece of iron or steel, then what we're going to do is put a material on top of that iron or steel that's anodic to it. So we zinc plate the surfaces. We put zinc paints on the surfaces, make sure that we get a little electrical connection with the flake part of the zinc touching the metal. So we can have a little current to flow. Or if we want to, we can do alloying, and that is to say we're going to put something in the metal now that will cause a passive film to develop on the surface, and then we won't have to plate it, and we have these things that are called as stainless alloys, like the stainless steels.
Wire mesh will corrode first at points where wires cross, for two reasons. First, iron oxide is cathodic to iron. Secondly, the oxygen in the water cannot reach the crossover points well. This is known as a concentration cell. Plastically deformed material becomes anodic to metal that is not deformed. An example would be serial numbers stamped in metal. To prevent corrosion in underground piping, more active metal anodes are electrically connected to the pipes so that they corrode rather than the pipes.
Well, this is a tremendous subject, and the protection story is one that's all important to us, because $60 billion a year to lose in our economy is just too much. And we have to make sure then that we do a good job of getting out there, protecting everything we have. Well, we still have another thing to look at. We've got to look at all of the metals in service, because corrosion is not the only thing that happens, and we'll do that in the next lecture. Thank you.